Last time we introduced the idea of memory management, and we talked about the issues revolved around it. We talked about soundness. We talked about the efficiency of. We talked about the efficiency in terms of time and the efficiency in terms of memory. What we'll do today is we'll talk about the first main technique that is used for memory management. This is, in fact, for automatic sound memory management. So, automatic sound memory management has a more colloquial term, which is garbage collection. So the key idea of automatic sound memory management is that your program does not need to contain free in it. It does not need to contain retain or release or anything like that. You just write your program assuming that you have infinite memory, and everything is just taken care of automatically. Now, the key idea to how to take care of things automatically is to understand what objects can be freed. What can be freed? Now, on one hand, as we talked about before, in principle, something could be freed if you won't actually use it. But it's not possible to figure out what you won't actually use unless we had some way of solving, basically like the halting problem, where we could look at some code, figure out that it's never going to return, and then thus we can free everything after it. Most people tend to think that when variables leave scope, they may be freed. But actually, this is not true. And it's not true because of aliases, which we talked about before, where a variable may mention something now, and something else may point to it. And so instead of either focusing on the scope of a variable or on some intrinsic notion of being used, instead, with automatic sound memory management, we use a concept called reachability. And here's the idea behind reachability. Imagine that we have some object in memory somewhere. This thing is reachable if the program could get to it. Now, how could it get to it? It could get to it because maybe there's some variable that is directly pointing to it. So we'll say that reach O, an object is reachable if and only if there's a variable that points to that object. Okay. The next thing is that maybe there isn't a variable that points to it, but maybe there's a variable that points to a pointer, and that pointer points to it. Okay, which means that there's some variable where inside of it is a pointer. So that means that it's either a variable or there is a pointer that goes from that pointer to the object, and the pointer itself is reachable. Okay? So what's next? Well, it could be the case that maybe it's not a pointer, but in fact this thing is a field. So maybe there's some other object that we'll call field O prime, where O is a field of O prime, and O prime is reachable. Or maybe this object O is sitting inside of a register, meaning that it's like a temporary value. You know what I mean? Like if I write 1 plus f of 2, then f of 2 gets computed, and then it's sitting there in a register somewhere. Or it's on the stack. Okay? In essence, the idea is that reachability means that you could have written some program expression, and that program expression could have named this particular object. And if that could have been written, then that means that this object is reachable. And here's the rule. Unreachable objects may be freed. All right. So how can we define what is reachable in terms of the in terms of our model of the CEK machine? Well, it's a little bit difficult to do that right now because we don't have a good way of talking about what exactly is in memory in our CEK machine. Because recall that our CEK machine states look like this. There's an expression, there's an environment that is a mapping from variable to value, and then there's the continuation. What we could do is we could use the CESK machine, where we have an expression, we have an environment that maps variables to locations, a store that maps locations to values, and then what we could do is we could have continuations themselves. Really, we could basically, we could sort of make it so that everything, in fact, yeah, let me just elaborate on this a little bit. Rather than have an expression here, oh, gross. Rather than have an expression here, we could have that be a location as well, which is the location that the expression is stored at, and this continuation would itself also be a location. Now, we would leave the rules mostly the same. Basically, the main thing that would be different would be when we call a function. So let's imagine that we're calling a function. So we have some value v, and when we write here v, I don't mean, what I'm saying is that inside of this location in the store. Okay, let me be super precise. All right. So we used to have a rule that said this. We said v environment, and then there was a k app, and the k app had a closure, and the closure had a lambda xe, and then there was some saved environment, environment prime, and then there was an environment prime, which is the one that was saved, and then there was a continuation. Okay, and then what this did is that we went to E, that's the body, with environment prime mapping X to V, and then we had K. So that's the rule that we used to have. If we wanted to be super precise about memory, what we would do is something like this. We would say, well, there's pointer 1, and then pointer 1, an environment right here, a store, and then pointer 2. Okay, where pointer 1, where store of pointer 1 was equal to some value v, and where store of pointer 2 was equal to k app of pointer 3 and an environment prime and pointer 4. Okay, and where store of pointer 3 was equal to closure of pointer 5 and environment prime. All right, and where store of pointer 5 was equal to lambda x dot e. And then what this would do is it would then go to E, that's that guy there. Oh yeah, this is gross. Because a lambda would really be a lambda with x and pointer 6. Okay, so then what we're going to do is we're going to have pointer 6 here. Then we're going to have a new environment, which is based on environment prime, that's that one, that maps x, that's the variable, to a new thing, which would be pointer 7. And the continuation would be pointer 4. Sorry, and we gotta say store prime, where store prime equals store, except that pointer 7 goes to v. So we could make a version of the CEK machine that was extremely particular about what exactly happened with memory in every single situation. That would be super, super tedious, but we could do it. Then what we could do is we could talk about which pointers are reachable. So we could define a function called reachable, and it would take as an argument an expression pointer, it would take an environment, it would take a store, and it would take a pointer to a k. And essentially what it would do is it would look inside, it would say that that this pointer is reachable, it would say that that pointer is reachable, and it would say that everything, all the pointers inside of the environment are reachable. It would ignore the store. Then it would do is it would recursively compute, okay, well, given that that's reachable, that means that everything that it's pointing to is reachable. Given that this is reachable, everything it's pointing to is reachable, and so on and so on. It would compute what reachability means. So essentially what we would have is we would have this big network of objects in memory. Okay, so I'm just drawing a bunch of objects. And some of them would be pointed to by the expression position. That's that part. So maybe this one is pointed to there. Some of them would be pointed to by the environment. Maybe this one and that one. And some of them would be pointed to by the continuation. Let's say that one. Now, maybe the expression is pointing to here, and maybe the continuation is pointing to there, and the environment is pointing to there, which points to there. And maybe this thing right here is a continuation object, so it's pointing to that. Okay? So our memory is going to look like this. There's going to be a bunch of objects, and some of them are being pointed to by the program. Okay? Some of them are being pointed to by the local variables. And some of them are pointed to by the stack. And this is true in any programming language, not just in our CEK machine model. Variables are either pointed to by the program, they're pointed to by local variables, or they're pointed to by the stack. I suppose that there's one more thing that could be the case in a language like C, which is that they could be pointed to by registers. And registers are kind of like the program. All right. So once we have a graph like this, how can we figure out everything that's pointed to? The key idea is to say, well, if this is pointed to, let's like put a little mark on it. Let's like fill it in. And then we'll fill in this because it's being pointed to, this because it's being pointed to, this because it's being pointed to. And then we'll just do this recursively. So we'll see that that's being pointed to by this one's being pointed to, that one is, and then that one's not. And then after we went through and figured out everything that was being pointed to, then we could go back and delete all the things that weren't being pointed to. This strategy is called mark and sweep. How it works is we first trace all objects from the root set, and the root set is globals, locals, the stack, and so on, marking a single bit. Then what we do is we walk all memory, and we delete things with no mark, things without a mark. And then if they do have a mark, then we unmark them. So otherwise unmark. And the reason we're unmarking them is because we want to make it so that next time we go through, they won't be marked, so we'll be able to, learn from whether they've been marked or not. All right. So this key idea of mark and sweep is quite simple. We start with the root set, the things that we know are reachable, and then we just follow all the things inside of them. Now, there's a whole bunch of issues that show up when trying to implement this. And let's just go through them. So the first idea is, given a pointer, what is it pointing to? In other words, we know, for example, that this object is being pointed to. But why do we know what's inside of it, right? Like, imagine you're a C program and I just told you pointer 80. Well, you don't know what kind of thing is stored at 80. So what this means is that the memory manager, the GC, needs to know the structure of memory. Now, there are lots of techniques for doing this. Imagine you're in a language like C++. Well, when you point to an object, the very first thing that you're pointing to is actually its vtable, and you can use its vtable to figure out what kind of object it is, and thus what its structure is. In other languages, like Python and Racket or in our language, there's only a small set of values that are possible, and so from those we can know what their structure always is. The next thing that we need, and so once we know what kind of thing it's pointing to, that also allows us, when we're sweeping through memory, when we literally walk through every address, we start at address 0, and we know what kind of thing that is, so we know that it's, say, 20 bytes, so we can skip over the next 20 bytes and go to address 20. Look at what kind of thing that is, and skip over. Okay. This is actually kind of a big deal, because one thing that you'll notice is that with C programs, you can't know what their structure is unless you do something extra to keep track of it. Like if you are implementing your CK machine, you need to do something like a tag field to figure out what kind of thing something is. And that's not going to be immediately apparent to your C compiler. So the point here is that to implement a mark and sweep algorithm, you need to communicate information from the program to the memory manager, specifically the shape of objects. All right, what's another issue? Another issue is, how do you walk the stack? How do you inspect the stack? So if you're implementing something like the CK machine, well, the continuations are just more objects, so you walk them exactly the same way. But if you were to actually use the program stack, like the one provided by the CPU, then you're going to have some way of looking at what address you're on the stack and then understanding the structure of the stack frames. That's something that's not a given. That's not like automatically available in C code. So if you were to write a compiler for your programming language to, let's say, assembly, and you're going to use the stack, you need to make it so that as part of every stack frame, you have information about where on the stack things are pointers and which ones aren't pointers. So that's another issue that's important for really implementing it. So the next thing to think about is, like, how do you mark? So how do you actually mark something to say that I've seen this before? Now let's imagine that every object starts with a byte, where that one byte stores what kind of thing it is. Well, that means that you have 256 kinds of things. And even a language with tons and tons of different types, like Racket, doesn't have 256 different kinds of things. So typically what you do is you take a single one of those bits and you say, this bit is for marking. And so that means that you can only have 128 different kinds of things, and then that one bit is for whether it's been marked. So that's kind of a strategy that's pretty common. There's another idea for marking that's called Bebop. And Bebop stands for a big bag of pages. And the idea of big bag of pages is that rather than allocating memory so that you could have a cons that was right next to a number that was right next to a string, instead what you do is you allocate an entire block of memory that is only for strings, and another block of memory that's only for conses, and another block of memory that's only for numbers. Then what that means is that now you don't have to store the tags next to every single object. You can store them one time at the front of the page. Then what you can do is you don't have to store the marks next to each object. You can have a bit mask at the front of the page. So for example, imagine that you had a page that was 4K of memory. You could use 1 byte to say what kind of thing it is. Then let's suppose that all of those objects were like 4 bytes. Well, that means that you can store 1,000 of them. And so then what you do is you say, okay, well, there's 1,000 of them, and 1,000 of them means that I need 1,000 bits. And so what you do is you then have your 1 byte for the object, for the tag, and then 1,000 bits, which is just a bit mask for which ones have been marked, and then now you can compress all the space that you need. So Bebop is a strategy for doing that makes an extremely efficient way of keeping track of the marks. All right, so let's talk about the next thing, which is that the various overheads of doing mark and sweep. So mark and sweep. Oh, sorry, one last thing, which is actually, I guess it is appropriate to talk about this. So the overheads. So mark and sweep. So what are the expenses? Well, we're still going to call malloc, all right, because our code is going to do allocation. It's not going to call free anymore. Well, you're not going to call free, but it is going to call free. It's going to call free as it's walking through memory. It's also going to do a marking phase, and it's going to do the sweeping phase. Okay, so how expensive are each one of these things? Well, first of all, marking, we know that it's going to look at every single live object. So that means it's going to be O of the live objects. Because whatever it's going to do, it's going to do it once to every single live object. Now, what about sweeping? Well, sweeping, we know that it's going to look at all of the live objects and all of the dead objects. So it's going to be O of live plus dead. In other words, it's going to look at all of memory. It's going to be O of all of memory. Now, what about malloc and free? Essentially, the most efficient way to do mallocing is to store your free list as a tree of the size of all the different slots of memory. And then what you want to do is you want to search inside of that tree, and searching inside of that tree is going to take log n time. So our mallocs are going to be log n. Now, what about freeing? Freeing essentially would be inserting into that list. Now, inserting into the list would be O log n. But it turns out that we can actually get away with considering this to be, for our freeing to be free, because we know that every time we do sweep, we're going to discover every space that's free. We're going to basically reconstruct the entire thing. And it turns out that it's actually more efficient to create a sorted list from nothing than it is to take one and then randomly insert into it. So in fact, constructing the free list is going to be included in the sweep phase. So overall, the performance is going to be, for time, it's going to be live plus memory, and for mallocing, it's going to be log n. And then in terms of space overhead, it's really hard to quantify the space overhead, but essentially all we need to do is we need to store the free list, and we need to store the marks. And so that is and the tags. And so those are both very efficient. There's no extra copying what we need to do. In practice, mark and sweep tends to have space overhead that is much, much lower than doing manual memory management. Now, what about pauses and latency? So in terms of time, we do have to pay for the live and the sweep, the marking and the sweeping, but it turns out that there's a strategy for doing this real time. So real-time strategy exists. And recall that when I say real-time, what I mean is some way of arbitrarily decreasing the size of the pauses. So there's a huge number of different techniques for implementing mark and sweep efficiently, where essentially what you can do is you can have a trade-off between how much memory overhead there is and how short the pauses are. If you have long pauses, then you can make the space overhead low. Because essentially the idea is that the more frequently you do mark and sweep, the more often you'll find things that you can free. And if you do it more frequently, and you of course look over every single object, then that means it's going to take a long time. On the other hand, We also have figured out a way to make it so that mark and sweep can be made entirely incremental. So I'll write here incremental. Where when I say incremental, what I mean is that we can do like 10% of the marking phase and then totally stop, let your program run, and then do 10% more of the marking phase. And then once we've done 100% of marking, then we switch to do 10% of sweeping. And so what that means is that you can pick any number. You could say, I want my mark and sweep to only take 1 millisecond. And so you just give it 1 millisecond at every certain rate, and it will be able to manage your memory. And if you only give it 1 millisecond every 30 milliseconds, well, then it's going to use more memory than it would otherwise. But you can basically change these numbers arbitrarily. You can say how long you want it to run and how often, and it will always work. And so mark and sweep is kind of optimal for space, and optimal for latency. But it is not optimal for time. And the key reason it's not optimal for time is because malloching is still log n, and the sweeping phase takes O memory. You may say to yourself, what could be better than O log n? Well, maybe you don't say that because maybe you don't realize that right now, if you're using, when I say right now, I mean if you're using like C or C++ or something like that, and you're calling malloc, it is costing you log n. That is how long it takes to do a malloc. Plus, if you're doing a copy afterwards, then that is O in the size of the memory that you're copying. So memory management is extremely not free when you're doing manual memory management. And mark and sweep has the same time performance, but is sound, except for these sweeps every once in a while. What we'll talk about next time is a much more efficient strategy that is much more efficient for time. Yes, it's more efficient for time, but the trade-off will be that it's going to be slower, it's going to be worse for memory. So we'll talk about that next time.